Symmetric identity. You are still on quadratic equation and root whatever. Symmetric identity. So this one is in your textbooks, right? You have to know it. Without it, you cannot solve for the roots. So when we say symmetric identity, we are saying that if alpha and beta are interchanged, the functions still remain the same or multiplied by -1. Symmetric identity. With our first proof, alpha squared plus beta squared, that's what we may have. This alpha plus beta squared, if we expand this, alpha plus beta squared, so this is what we get it, right? Now, so this alpha property, so alpha times the whole of this, beta times the whole of that is the distributive property, right? So if alpha times this, so still alpha times alpha is alpha square, alpha times beta is beta, alpha beta, then beta times alpha, alpha beta, beta times beta, beta square. Good. Now we have beta, alpha beta, so that's why we get 2 alpha beta. Good. We are saying we are approaching somewhere. Now you want to get alpha square plus beta square. That's the main thing. So this alpha square plus beta square plus 2 alpha beta. So therefore our alpha square plus beta, we will subtract this from both sides. So if subtract this from both sides, we move it across or the equal sign. So if subtract it from both sides, here we go to this is what you get. So alpha square plus beta square is what? Alpha plus beta square minus 2 alpha beta. This is the proof. Alpha square plus beta is alpha plus beta all square minus 2 alpha beta. So it has been proved. Good. So let's see. So we know this proof, right? So take note of this proof. So let's move on to our next proof. In this proof, the proof 2, alpha minus beta all square. We said that you get alpha plus beta square minus 4 alpha beta. How? So let's prove this. Right. Now, we know that alpha minus beta square the same as alpha minus beta, alpha minus beta. So we are using the distributive property. Alpha times the whole of this, negative beta times the whole of this. So alpha minus beta square, we get alpha square, then alpha minus beta, beta minus alpha, then negative beta times negative beta. We get what? Positive beta square. This is what we get. If you simplify this, we get this one. So let's move on. Now we have what? Negative alpha beta minus negative alpha beta. So this one, if we divide, we get negative 2 alpha beta. But it's negative and negative, yes, the negative 2 alpha beta. Okay, so we are approaching somewhere, right? Alpha square plus beta square minus 2 alpha beta. Now we know what is alpha square plus beta square. Do you remember? We prove it. That's the first proof. And we said that one, when you prove it, we got what? Alpha plus beta all square minus 2 alpha beta. Do you remember? Yes. So we use that one. But this is this. That's what I was saying. That's our first proof. So we just substitute it in there. Where we see alpha square plus beta square, we just substitute this one there. So we have substitute this one here. So therefore, this one can be solved. So it has been proved, right? So alpha plus beta square minus 4 alpha beta, because negative 2 alpha beta minus negative 2 alpha beta is equal to negative 4 alpha beta, and it has been proved. So let's look at our third proof. Yes, this is our third proof. We know our second proof. Our second proof was alpha minus beta all square. So if you know the second proof, you can do the third proof. Equals alpha plus beta square minus 4 alpha beta. So therefore, if we want to tell, we take the square root of both sides. Therefore, our 2 will go. So let's see. Right? So we take the square root of both sides because we know this, that alpha plus beta square. So this square will go from our second proof. So therefore, it has been proved. So from our second proof, we can prove this one with easy. When we take the square root of both sides, we can get this. So our third one has been proved. So this is our fourth proof, right? Alpha square minus beta square. And how do you call this? Yes, perfect square, right? So it's one alpha plus beta times alpha minus beta. This one we know. So it's easy as that. So this one is easy. Alpha plus beta times alpha minus. So let's move to our fifth proof. Now this. So therefore, our proof alpha plus beta cube. So if you expand this, you get this. How will we get this? Yes, this one you can use your Pascal triangle binomial theorem. Coefficient will be 1, 3, 3, 1, right? Or you can just simplify this. You can start from alpha plus beta square. The answer that you get, they used to multiply alpha plus beta. You get this expression too. So you can try it, okay? Let's continue. We know that alpha cube plus beta cube. So let's arrange it. This is what we have got. So what should we do here? Yes, there's any magic here. We can still do some magic here. What should we do? We will factorize something here. Okay. Now, alpha cube plus beta cube. This is what we want. So 3 alpha square beta plus 3 alpha beta square. If we factorize the alpha beta out, we get alpha plus beta, right? So 3 alpha beta out, because there's 3 here, there's 3 here, there's alpha here, there's alpha here, right? There's beta here, there's beta here. So if I factorize alpha beta out, I'll get alpha plus beta. Okay, if multiply to, you get this expression, factorization. Therefore, we are approaching our proof. This is what we are looking for. So you then maintain this and move this one across the equal sign, right? Good. Then it has been proved. Simple as that. So you have to know your symmetric identity and the proof, so that in the examination hall, you know. So let's solve some example. Since we know our identity, we can solve example. Without identity, you cannot solve example under this. So please know the identity. Okay. So if alpha and beta are the root of 2 s squared minus s minus 2 equals 0, find the value of the following. 1. Alpha squared plus beta squared. You see, if you don't know how we solve this, so because we don't have any alpha squared plus beta squared, you have to know the identity, right? This one is our quadratic. So let's compare. Our a here is 2, our b is negative 1, c is negative 2, right? So our sum of root, that's alpha plus beta, is negative b out of a, which we have proved it in our previous video. So you can go there and look for it. So negative b out of a, they know our b and a. Therefore, our answer is 1 out of 2. Then I'll put that alpha times beta is c out of a. They know our c here and our a here. Good. Now, what should we do? The main question. Alpha square plus beta is alpha plus beta square minus 2 alpha beta, which we have proved. So we know our identity. So we just do the substitution here because alpha plus beta is the sum. Our sum here is half, and then our product here is negative 1. So we just substitute in there, then you find it. So the answer is 9 out of 4. Let's solve one example here. So you can do this one for me. This one you find the LCM because it's in a fraction form. So our LCM of alpha square beta square is what? Yes, alpha square beta. Alpha square beta. Now, alpha square beta goes to alpha square. It will lead to beta square. So the beta square here, the beta square that we left here, times the one up, which we know in the primary school. So beta square, we get beta square, plus alpha beta square going to beta square, we get what? Alpha square times the 1. That's why we got alpha square. Now, beta square plus alpha square, we know that is alpha square plus beta. That's why we say it's symmetric identity. I said if it can be interchanged, but it's still the same. The function is still the same. So, alpha square plus beta square, we know that is alpha plus beta square minus 2 alpha beta, right? And this one, alpha square beta square, is alpha beta all square, which means we can do our substitution here with easy. So if you substitute this, you will get this. So we know that our sum is half, our product is -1. Therefore, this is our answer. Subscribe to Symmetric for more videos. Bye bye.